Let's talk systems of equations with three variables. In the past, we've talked about two variables, an x and a y, and therefore two equations. Today, we're going to discuss when we have systems with three variables. When we have three variables, we must have at least three equations. Now, the graph of a linear equation is with three variables is actually no longer a line. It is a plane. So when we talk about our solution to a system of three variables, we still have three different options: a single solution, a point, infinitely many solutions, or no solutions. However, there are more scenarios. So to have a single solution, it's where the point in which all three planes intersect. Now, that point is what we call an ordered triple now: x, y, and z. So we're looking for three unknowns. For infinitely many solutions to occur, there's two scenarios. The planes could all be the exact same and be on top of each other, or the planes could intersect in a line. Remember, lines extend in an infinite direction, so therefore we have an infinite amount of solutions. The last scenario is no solution, and that's with three different cases. Remember, a solution is where all three planes intersect. Therefore, if only two intersect at any point, it would not be considered a solution to the entire system. So even though in the first picture we see some intersection crossings, there's never a point where orange, green, and blue planes all intersect. So therefore, there's no solution. Same with the second. There's never a point where all three colors touch at one point at any time. And the third one is pretty obvious. There's no intersection at all amongst all three. They're parallel to each other. So therefore, again, there's no solution. So how do we solve these systems? Let's start with our first example. The way we're going to solve this is to use elimination and to try to narrow it down to two equations with two variables. Okay, so our goal is to narrow down to two equations with the two same variables. So if we look at our first example, all three have three variables. So we need to try to get rid of one of the variables. And you can choose. If I look at all three of these, I'm going to pair two of the equations together. I'm going to pair the first and second together. And I like to stay organized. So I'm going to pair the first and second pair together. I'm going to write them on top of each other. X minus 2y plus z equals 15, and 2x plus 3y minus z equals 7. When I have those two equations, I notice that the z's are opposite of each other. Therefore, if I combine these using the elimination method, I'll now have an equation with two variables. My z's disappeared. So again, my goal is to narrow down to two equations with two of the same variables. I have one equation now with two variables. I want to create a second equation. Notice I got rid of z's, so in my next pairing, I also need to get rid of z's. Let's look at what may be easiest to combine. I combined first and second. This time, I think I'm going to combine first and third. By combining first and third, what we need to do is we need to multiply that first equation by 5. This will make the z's be opposite. Now my first equation is 5x minus 10y plus 5z equals 75. Our third equation, we will leave as is. I'm going to put those together. When I put those together, I get 9x, and look at this. My 10y and my 5z actually happen to cancel, and I get 75 minus 3, which is 72. This is an awesome situation because by combining those, now I can already solve for x. I can keep on going. X will equal 8. Woohoo! We have found one variable, but I still need to find y and z. Well, I can go back to the equation I found with the first and second and find y because it just contains an x and a y. So now I'm going to substitute in over here. 3 times 8 plus y gives me 22. 24 plus y equals 22. Subtract 24, and y will equal negative 2. We now have our x and our y, but we need to find z. To find z, I'm going to substitute into one of the original equations. I'll substitute it right into the first because z is positive and alone there. So x minus 2y plus z equals 15. I know x is 8, y is negative 2, and we're looking for a z. This would become 8 plus 4. So I would subtract 12, and z would equal 3. Therefore, my solution is the ordered triple of my x value, my y value, and my z value. And there you have it. Okay, what would have happened if this didn't eliminate? If I had left with an x and a y here, I would now have two equations with an x and a y, and I can go use substitution or elimination. Okay, let's look at number 2 together. If I look here, again, our goal is to narrow down to 2 equations with the 2 same variables. Well, our first equation has 3, our second has 3, but good news, some of our work is already done. This third equation already has just 2 variables. The x is gone. So what I want to do is I want to pair the first and second equation together, and I want to eliminate x. By doing so, we'll keep the first equation, but I will multiply the second equation by negative 2. This gives me negative 2x minus 4y plus 2z equals negative 16. When I combine those, I get negative 5y plus 5z equals negative 10. Now what I have here is a system of 2 equations. This new equation of negative 5y plus 5z equals negative 10, and the third equation, which was 2y plus z equals 1. From here, I can solve using substitution or elimination to get rid of another variable. Let's multiply the bottom by negative 5. Again, I'll have negative 5y plus 5z equals negative 10 for the top, but now I can have negative 10y minus 5z equals negative 5. I'll put those together, and negative 15y equals negative 15, so y equals 1. I have found one variable. We need to go find the others. The question is, do I go find x or z next? Well, I'm going to go find z next because I have a system with just 2 variables, and if I know y, I can find z. So I'm going to use 2y plus z equals 1. So 2 times 1 plus z equals 1. This would give me that z equals negative 1, 1 minus 2. Lastly, I will solve for x by choosing one of the original equations. I'm going to use that second original equation. So x plus 2 times 1 minus negative 1 equals 8. X plus 2 plus 1, so x equals 5. Therefore, the solution to the system is 5, 1, and negative 1. Remember, we can always check our answers by plugging these back in. So this would be saying 10 minus 1 is 9, and then 9 plus negative 3 is 6, which is correct. I could plug it into the second equation. 5 plus 2 times 1, so 5 plus 2 is 7, minus negative 1, 7 plus 1 gives me 8. And lastly, 2 times 1 is 2, and 2 plus negative 1 gives me 1. Hooray, so we know that's correct. Okay, so again, our goal for systems of 3 variables is to use the elimination method to get down to 2 equations with 2 variables. Then you can use substitution or elimination to solve. Okay, now let's look at number 3. For number 3, we're going to go about doing the same thing. We want to get rid of a variable. You choose what might be easiest. I see right here we have a pair of opposites for x. So I'm going to pair the second and third equation together, and I'm going to try to eliminate x. So negative x plus 3y minus 2z equals negative 1, and x minus 2y plus 3z equals 1. When I put those together, my x's will cancel. I will now have positive y plus z equals 0. Okay, so I got rid of my x's. Now I need to get rid of x's for a second equation, because remember our goal, get 2 equations with 2 of the same variables. I now just have 1 equation. So I think I'll pair the first and second. For the first and second, we'll leave the first one as is. And I'll multiply the second equation by 2 so that our x's become opposite coefficients. Okay, I'm just double checking my calculations. It's really important that you take your time with these calculations because one little mistake could throw off everything. I'll combine those now and I get positive 2y plus 2z equals 3. Okay, now what I have here is a system with 2 equations, what I starred. So those equations are y plus z equals 0 and 2y plus 2z equals 3. How do I solve this? By using substitution or elimination, your choice. I'm going to use elimination, and I'm going to multiply that top equation by negative 2. This will give me negative 2y minus 2z equals 0, and then I'll recopy that second equation. I will put those together. My y's cancel and my z's cancel, so I get 0. And 0 plus 3 is 3. What just happened here? My variables canceled, and I'm left with a false statement. If I'm left with a false statement, what does that tell me? That tells me that there will be no solution. Therefore, in this scenario, we have the following situation. One of these things is happening where we never have a point where all 3 planes intersect. Sometimes you will find by just pairing 2 equations at the very beginning to cancel, and that makes it super nice because we would have no solution right away. All right, and last but not least, number 4. Let me separate this a little bit so that we have some work here. Okay, With number 4, we got a lot going on. Here's one thing I would show you is when you see like fractions and stuff, maybe clear those, make life a little easier. So would everybody agree that if I cleared the fraction here, this I would multiply by 2? So this is really the same thing as negative 2x plus 3y minus 4z equals negative 8. Okay, and we can think of it as those 3 equations. Now that I did that, let's pair up some of our equations. I'm going to pair up the first and second. And I'm going to eliminate x again because I see we have 2x and negative 2x. When I do that, you may have already noticed that not only are the x's going to cancel, but the y's cancel, the z's cancel, and even the constants cancel. So I get 0 equals 0. What does that mean? That is a true statement. However, I cannot be done right here and say infinitely many solutions because I only paired the first 2 planes together. Remember, I could have an intersection amongst 2 planes, but the third one may never intersect. Therefore, I cannot be done at this point. I have to compare that third equation in here before I can say we have infinitely many solutions. So I'm going to now pair the first and third. By doing so, I'm going to divide all of these by 3 because I see they have a GCF of 3. So that first equation is 2x minus 3y plus 4z equals 8. That second equation, like I said, if I divide by 3, this would give me 2x minus 3y plus 4z equals 8. I want a pair of opposites, so I'm going to multiply that by a negative. When I put those together, woohoo, we have good luck here. Everything is going to cancel again. So, because everything all canceled, comparing my first with the second and first and the third, that also means the second and third will have an infinite amount of solutions. So therefore, my solution is infinitely many. Remember, do not say all real numbers. We want to say infinitely many solutions. And it's not going to let me keep writing right now. Infinitely many. I hope that clarifies how to solve a system with 3 variables. What I'm going to ask you to do is to, of course, refer to these 4 examples as you try the following. Try this word problem. Remember, you are going to have 3 variables, and so you need 3 equations. I will help start this off for you and ask you to finish it. So at a theater, seats in section A closest to the stage cost $30, seats in B cost $25, and lawn seats cost $20. There are twice as many seats in B as A. When all 19,200 seats are sold, the theater makes $456,000. Determine the number of seats in each section. So right away, we need to define our variables, and there's 3 of them. There's the number of seats in A, the number of seats in B, and then the number of lawn seats. Because I have 3 variables, I now need 3 equations. Well, it says that there are twice as many seats in B as in A. Therefore, 2x will equal y. Remember, if there's more seats in B for the equation to be equal, we need to double the amount of A to make it be equal to B. We know that there are 19,200 total seats sold. So the amount of all of the seats equals 19,200. And lastly, we know that there was a sum of $456,000. If seat A costs $30, that would be 30x. Seat B is 25y, and lawn seats are 20. Here are my 3 equations. So now I ask you to finish solving the system to determine how many seats of each section there are. Once you have completed that, please try these 2 examples on your own.